So after spending probably a month on hypothesis testing with proportions, now let's change our attention to means with chapter 22. We know with hypothesis testing we must meet certain assumptions. Our data must be independent. So we have two conditions that must be met. A randomization condition, so the data must arise from a random sample or a suitably random experiment, like a simple random sample. If we sample without replacement, these selections are not independent. So if I have a deck of cards, I take one out, but don't replace it, then it changes the probability, right? And we also must meet the 10% condition. The sample is less than 10% of the population. Note what's missing. We are talking about t-test, so that's a hint there instead of the z-value. It was randomization, 10% condition, and there was something else that we normally do.
The failure.
Success failure, yes. It must have more than 10, right? Yeah. More than 30 samples. Well, since we're doing the t-test, you can have less than 30 samples. So that's why that's missing. Your sample size can be small. But if it is small, we need to make sure we have a nearly normal condition. Students' t-model won't work for small samples that are badly skewed. The data should come from a distribution that appears, keyword there, this is a judgment call, appears to be uninormal and uninormal and symmetric and without strong skews or very strong outliers. It can have some outliers, they just can't be way out here. So, here's an example. Data on the left is okay. Notice if I put my data in a bar graph, it kind of more or less represents a normal model, right? Mm-hmm. I do have a little bit of an outlier here, but notice it's not like way out here. So that outlier would be okay. This, we couldn't be able to use our t-test. Because notice how skewed this is. I have a very significant outlier here, and it's skewed to the right. Or skewed that way, yeah. Opposite of what you're saying, skewed. So this does not represent, where's my pen? Notice how it looks nothing like our normal model. This data looks okay. So we have to test those three things. Let's go through an example. Researchers test 150 farm-raised salmon for organic contaminants. Same as yesterday. We found the mean concentration of the carcinogenic insecticide Mirex to be 0.0913 parts per million with standard deviation of 0.0495 ppm. As a safety recommendation to the recreational fishers, the EPA recommends screening value for Mirex to be 0.08 ppm. Our farm salmon contaminate beyond the level permitted by the EPA. So let's first create our null and alternative. So this represents my mean. My mean equals what's going to be my value. Which numbers up here am I going to graph for my mean value that I'm testing against? The what?
The 0.08.
Very good. This will be my mean. So it should be equal to 0.08. And now for my alternative, do I want that to be more or less? Our farm salmon contaminate beyond the level permitted. So what I put, not equal, greater than, or less than?
Greater than?
Yeah, I'm saying my mean is going to be greater than this value, right? Beyond it. So we're going to use the greater than symbol. Now, let's perform the t-test using our calculator. The process is go to stats, test, t-test. So let's do a t-test value. Hit number 2. Do I have data or does it give me all the stats? It gives me all the stats. So my first stat here is, what is your null? What is your mean?
0.08.
0.08. 0.08. What is my average for the data?
0.0913.
Yep. 0.0913. What's the S value, my standard deviation?
0.05. I mean 495.
0.0495. And how many samples did I have? 150. And down here, what symbol did I use? I used the greater than symbol. Right there. And calculate. So double check your numbers. It'll be a shame if you got it wrong because the calculator doesn't make mistakes. You make mistakes. So 0.08, okay. 0.0913, that looks good. 0.045, that looks good. 150, okay. Greater than symbol. All right, now calculate. Gives me my t value, 2.7, well 2.8 I guess. My p value is 0.0029.
Yeah.
And it also gives me what I already put in. My mean, standard deviation, and n value. Oop, kind of gave away the answer. So I have a very, very small p-value, right? Statistically significant. This is less than 0.05, which is usually our normal alpha. Which means I can reject the null. And I conclude that Murex contamination level does not exceed. So I'm going with my alternative and saying it does not exceed the EPA screening value. I reject it. So stat test for our test in the mean with one sample, we want to use number 2 t-test. Any questions on that? Okay. Now what if you weren't given the statistics? What if you were given data you had to input? So let's apply the one sample t-test to the student sleep survey. 25 students were randomly selected and the number of hours they slept on average were recorded. 6, 7, 6, 7, blah, blah, blah. The Sleep Foundation says that adults should get at least 7 hours of sleep. Is the mean amount that the college students sleep at least as much as the 7-hour minimum recommended for adults? So let's look at here. Randomly selected, that's good. 10% of the population, or less than, well, I'm already picking 25, so that's safe to assume so, yes. And does it more or less fit with the normal model? You can do that with your calculator. Here's how. You're going to have to enter this data anyway, so you might as well check the graph while you're at it. So go to Stats, Edit, and put in all of those values. So all 25 of these values. Okay? Anybody else? Once, twice? Now, let's look at the table. Go to second y equals. So you see up here stat plot. Click on stat plot 1. So I'm going to turn it on. You also say off. Click on. Go down here and click on the bar graph icon, like so. It's going to use your L1 list with the frequency of 1 and the color blue. Fine. So your stat plot with plot 1 should look as follows. And then hit graph. Now, here's a hint. Let me set your graph to probably what it looks like. Notice I don't see all my graph, or it's not nicely centered. Click on zoom. Go down to number 9, zoom stat. It's going to zoom in right into your statistics. And put the values for you. And hit enter. Bam! Nicely centered and big so I can see it. Would you say this is roughly a normal model? Not too skewed?
Yes.
Yes, I would say this is good enough to proceed. All right, so let's go ahead and develop our null and alternative. My mean is going to equal what value? What am I basing my data on? A mean of what? 7. Thank you. 7 hours. That's going to be my mean. So u equals 7. Now, my alternative. Is that going to be greater than, less than, or equal, not equal to?
Less than.
Yep. At least 7 hours. So there's my null and alternative hypothesis. Now, let's calculate the p-value. Again, you're going to go on your calculator. Stats. Test. Number 2, t-test. Now, instead of stats, which we don't have, but you could calculate by hand if you want to, or you might as well hit data and let the calculator do the work for you. So hit data. Our mean is going to be 7. Our hypothesis mean is 7. We're going to use list 1, all the data we put in there. Make sure my value is that, oops, that's the wrong one. No, less than value. And then calculate. T equals negative 1.67, P equals 0.05359. Interesting. I see I have a mean of 6.64, standard deviation 1.075. So how about that? It calculates my mean and standard deviation for me. Now, if we're basing our alpha value as 0.05, that is my cutoff, can we reject the null? If your cutoff, your strict cutoff is 0.05, can I reject the null?
Yes.
Is my p-value less than 0.05? We'll start there. No. So can I reject the null? No. Is it really close? Yes. So, the p-value of 0.05 says that if the true mean of students' sleep amount were 7 hours, and I take samples of 25 students, it can be expected to observe a mean of 6.64 or less by random chances of 54 times out of 1,000, or 5.4 times out of 100. So this is saying, if I were to randomly select 25 students, their mean will be 6.64 or less 54 times out of 1,000 chance. Now, since our alpha level normally is 0.05, and we'll select that as so, then this p-value is not small enough, even though it's really close. It's still not there to provide reasonable evidence to reject the null hypothesis that is true if the mean is at least 7 hours. So I cannot reject the null, but it's close. If it's close, you have 2 options. Run a different test. So let's look at confidence interval. Now note, this is how you would test hypothesis with confidence interval. You would have your interval, and is your mean with the hypothesis in between the interval? Is it?
Yes.
Yeah. 7 fits in between here. Interesting. So the 90% confidence interval shows plausible values for the mean number of hours that college students sleep, and it does include 7. Since the p-value is very close to 0.05, it might be worth collecting more data to reduce the margin of error. Note that this does not say, hey, I found it works here, so I'm going to go ahead and reject the null. Not quite. I want to try to force test to work for you. If you find conflicting values or conflicting results from 2 tests, then your next option would be to do what? Collect more data. Because you're close. Let's see if collecting more data skews it one way or the other. Just so we can reduce our margin of error. This is what you would do if your data are borderline. Maybe by using 100 students, it would be more obvious to reject the null, or not. Questions on that?
No.
All right. So today's assignment is on my math lab, because that's the best place to go with